Welcome back, everyone. Now let's begin our first lecture. Our first lecture comes from Germany. Professor Dr. Thomas Deserno is a world-renowned expert in medical imaging and artificial intelligence. He currently serves as Vice President of the International Medical Informatics Association for Europe and has dedicated his career to advancing medical imaging technologies that bridge engineering and healthcare. Today, he will give us a general introduction to machine learning and artificial intelligence, laying the foundation for everything we'll build throughout this week. Please join me in welcoming Professor Dr. Thomas Deserno.
Yeah, good morning. The mic working? Yes? It's working? Okay, great. Good morning, everybody. It's a pleasure, as mentioned before, to be here. And to open the summer school, I think it's important to, get a basic of terminology and what we are talking about the next week in all these presentations. So the idea is to give you a general introduction to machine learning and artificial intelligence. What is the difference, where it comes from, and I have provided this lecture in several parts. We will start with an introduction. Then we will talk about expert systems, machine learning, deep learning, and general intelligence, and also the learning strategies we have. And then we will focus a little bit on application of artificial intelligence in the clinical routine, and of course end with some conclusions. Yeah, but let me start with the motivation, and that is really easy for me, as I am chair of the so-called Peter L. Reichert's Institute. Yeah, who was Peter L. Reichert's? You can see that picture here. It was captured around 1969, and actually Reichert's was one of the pioneers in medical informatics in Germany. Yeah, the first one who started to use electronic documentation and then data analytics with machines available at that time. Yeah, and the idea was to build systems for computer-aided diagnosis, computer-assisted detection, or computer-assisted diagnostics. Yeah, the differences are more in terminology, not in the meaning of all these systems. The idea is to use computers and data in order to support the physicians in decision making, which you can also name computerized decision support systems. And maybe you know the paradigm, the right information at the right time, at the right place, which actually was worded by Reichert a long time ago. And that is still what we are doing in medical informatics, a discipline between the physicians and the computer scientists. And I have learned that the audience here also is mixed. Some of you are physicians, some of you are computer scientists, or more technical oriented. And we have this paradigm which has been extended over the time to some additions. It's not only the right information at the right time at the right place. It's also, to the right person should read here, in the right form. And in the right form, that is also something, artificial intelligence and machine learning contribute. How to use these tools in order to summarize information, medical information from various input data. If we go for some definitions, what is medical informatics? And you can define medical informatics as the implementation of computer science to improve communication, understanding, and management of medical data, information, and knowledge. You might have heard already about this pyramidal visualization. We have data here in the bottom, which is then transformed into information and knowledge, and then in the last stage as wisdom. And this picture here, I think it's interesting because if you read here what is written here, that actually is decision making. And that was what I have mentioned in the introductions, the computer-assisted decision support systems. But what is decision making? It's simply the process of making a choice. So you can also say it's a sort of classification. And I will give you a brief introduction with the math or mathematics. And the equations here are not for the purpose that you should calculate it in the moment. What I want to show in the next few slides is that there is a well-established mathematical background behind everything we are talking about. Also the algorithms which have been implemented in neural networks and so on. And this here is a typical pipeline. Data pipeline, disregarding whether we are talking about medical image processing or signal processing, but also if you want to understand vital signs of humans and so on. It starts with the data, which usually is pre-processed, sort of filtering and things like that. And then we have the feature extraction, where it comes to a feature vector. That is the X here. And that is used for classification into car classes. And in order to have this classification done, we need to train our classifier. That is the usual way it works. And for the training, we need sample vectors with known classification. That is what we need. And that here is the math behind, and then we can understand the decision making. We can define the different probabilities and also the Bayesian theorem, which I will not go in the detail, but it's just to get you the feeling that you can really calculate these things. And the question is, if we now seek for the optimal decision maker, what is the optimal classifier? We can use mathematics in order to calculate that. And in computer science, we usually define a cost function. So if you do a good decision, costs are low. If you do a bad decision, costs are high. And then we end up with the cost function, where K still is our real class and C is our class. And then it's clear if the classifier is doing it correctly, that means he did the right decision. Cost will be 0 or at least smaller than the costs if the classifier says I cannot decide it. And then the classifier could do the wrong decision. And usually you have the cost function defined such that the costs are definitely smaller if you're not doing the wrong decision. And then you can calculate the total costs, which is the sum of all these costs, and then you can try to minimize, and here is the mass, and it's all just the different equations and so on, and you end up with what is called the Bayesian decision rule. I will not go that much into the details here, but still this term is quite complex. Yeah, so how to get further? And the idea is, well, you do some assumptions on this L, the cost function. Yeah? And the first assumption you're doing in order to simplify that is symmetry. That means you say, well, if I assign the wrong class, so suppose the real class is number 3, and you say it's 2, then it's the same as vice versa. And this symmetry, we will come back to this thing later. If you think of the physician, you are familiar with the concepts of sensitivity and specificity. I will come to that later also. But if you want to find persons who are ill, and you have a person that is ill, but you decide the person is not ill, and then you have a person that is not ill, and you decide that person is ill, it might not be the same value. But here, in this mathematics, you assume symmetry. And further, you assume equality. That means all errors count equally. So that is what I just mentioned. The problem. And the third one is that you usually do not allow this rejection class here. So you end up with a binary problem, true or false. So keep these 3 things in mind, which are assumptions that might not be actually always the same. And then we end up with what is called the Bayesian classifier. And that is the equation you usually know as, well, what is the optimal classifier? But it is not optimal in terms of our reality because of the assumptions we are doing. Once I have done the decision, maybe with some computer support, I can, try to measure my performance. And these performance measures are all based on these 4-field matrix, where you have the true positive decisions, the false negative, the false positive, and the true negative. If we are doing the right decisions, we are in these 2 fields here. And here again, we have this type 1 and type 2 error, which might not be really equal in every medical problem. And with that, we end up with measures for precision and sensitivity, specificity, and accuracy, which are all defined based on these 4 fields here in the confusion matrix. And we usually describe the performance using what is called the Sieber operating characteristics, or RUC curve, which is a graphical visualization of the error we make. So suppose these are the distributions for actual negative, which are also negative predicted, and these are the actual positives, which are also positive predicted, and this is my threshold. And depending on where I put the threshold here, I change in between the error 1 and error 2, but I'm not always errorless. And the sensitivity and specificity values, of course, depend on where I put the decision. And so we use this ROC curves, in particular the area under the ROC curve. We have the 1 minus sensitivity and the specificity on the y-axis. If you do a random classification, just by using Würfel, what is it in English? The device with numbers 1 to 6, and do it like this. Your decision, say all the odd and all the even numbers are the binary decision. You will end up with a classifier on that curve here. this curve here would be the perfect classifier, and so you say, well, the performance of the classifier depends or is described by the area under this ROC curve, where the area being descriptive here. Okay, so that was just some brief introduction, and now we want to define what actually is artificial intelligence. And you can say artificial intelligence are computer systems which are capable of performing complex tasks that historically only have been, well, performed by humans. So, for instance, decision-making or problem-solving. And when it started with artificial intelligence, actually, we started in the 60s, or even before that, with what at that time was called expert systems. These expert systems, as you can see here, were low in complexity, and the data actually was rules defined by humans. Based on experience. So you need to you need domain experts who say, well, if the temperature is higher than something, decision is fever or not. And so the difficulty here was to engineer this knowledge into rules. But these systems have been built here, and the data curation, that means defining this knowledge, was actually high. And then in the 80s, that is what I actually, I was already in the study program at that time. It comes to machine learning, and that means we change from these rules to data-driven systems. And the idea was to discover things, and the first still was rule-based, but also networks, neural networks for decision making. Again, 20 years later, it comes to what we call deep learning. Here, the data we have in complexity is pretty high. We need a lot of data for machine learning systems, and in particular for deep learning systems. So we end up with these deep networks. The scope was not was more to sense, using sensor providing this data, and we do not do that much manual curation of the data anymore. We use the data as it comes, and then a couple of years ago, with all these GTP systems, we end up with something which is called general intelligence. The data in complexity is super high. We use almost everything for the training, and the task is more understanding than sensing by the means of pre-trained networks. So that roughly is the thing, and we will now go through the different areas from expert system, machine learning, deep learning, and general intelligence to understand the difference between these systems. So as I mentioned, in the expert systems in the early years, say it that way, knowledge engineering was the main thing, which ended up with what we call decision trees. So if you look to clinical guidelines, maybe as a consensus of experts in a particular field, how to cure particular illnesses, they end up with rules like if then else. If you have fever and your things like this, then do that. And just to illustrate that, it's German, but this is taken from S3 guideline that are in Germany consensus guidelines with a lot of disciplines involved, and they give instructions to physicians how to cure things. And if you look to the thing here, so there is a question, and then there is a decision what to do. So if then, and that follows And yeah, if you want to do that, you need to do this knowledge engineering, and you end up in what is called a decision tree. Yeah? And a decision tree is a flowchart-like structure for decision support. Now we have nodes. We start with a root node, and then we have internal nodes, we have branches between the nodes, and then we end up with leaf nodes. And algorithm in order to find such a decision tree is actually that you recursively use the data, and you aim to create pure leaves, belonging only to a single class, and then you evaluate different splitting conditions in the node you're actually in, and do a brute force. So that means you can, in any decision building the tree, you can try everything and look which is performing best, and then get to the next step. And as a result, you will end with something like here. That is a decision tree for prostate cancer. And still, it's a binary. You decide between the high risk and the low risk group. And the tree is check the first parameter, and depending on this, you assign classes, and you see that in this one here, all these classes or the leaves are not really perfect. Still, there are some portion of misclassified things there. But anyway, that is how these decision trees have been working. In a training phase, we need to determine the topology and also the thresholds, which of course can be different, ending up with complete different trees. And the key questions we need to answer in that building phase is, what is checked in a node, and do I terminate or continue with splitting? That means extending the tree. And after that, you might end up with a structure like this, which can be also easily implemented in a computer program, just following these rules. The advantage of these decision trees is they are easy to understand and to interpret. They handle both categorical and numerical data, and the tree visualization is intuitive and gets you an understanding of how the decision is made by the machine, or the decision support is made by the machine. Of course, that also have disadvantages. It is prone to overfitting. I will come to that term in a moment. And small changes in the data might you end up in complete different trees. What is overfitting? Well, in machine learning, we need this training data. As you remember, also in the Bayesian classification, there was a training data set. And it might happen that the model you learn, learns too much the specific training data, which is not really reflecting reality. And that means if then you use your model in order to support decisions from real-world data, it might not work that good. It only performs good on these data it learns from. Okay, so these were the early expert systems, and then in the 80s we had these machine learning things. And the classifiers used there are random forest, the Bayesian classifier, of course, nearest neighbor as a very simple thing, support vector machine, you might have heard about that already, and then of course the perceptron. The order here is not historically. I will start with random forest classifiers because they are based on the decision trees. So what is a random forest classifier? Well, it's a forest, as the name says, a assemble of trees. And Yeah, so we have multiple decision trees, hoping that they improve the prediction accuracy and stability. And what is the randomization in the name? Yeah, so we understand the forest, but how is the forest built actually? And that is using randomization. And there are two things we randomly alterate. The first is the data. That means we do not use the entire training data for each of the trees, but we randomly take a subset of that training data for each tree in the forest. That means each tree in the forest has a different data it is trained on, and also it means that some data points might be used in different trees. And the second one is regarding the features. At each node of the tree, we do not use all the features of our feature vector. We randomly select features for the classification. And doing that, we can build this forest, and then the prediction or the classification is simply done using the majority of trees. So the class, the forest predicts is that class where the most trees in the forest say that is the right class. And the second one is a Bayesian classifier. I already introduced that before. And there was a symmetry, equality, and dichometry, which I pointed out that are the reason why we have all these different classifiers. Because the situation where Bayesian classifier really is the optimal classifier is not really our real world. It's a more or less constructed mathematical thing, but still, the what is called naive Bayes classifier, that is one simplifying the computation, assuming that the features are independent, which of course they are usually also not, and assuming that the features are Gaussian distributed, well, which is an assumption you can do with a central limit theorem, but it's not clear whether these assumptions are fulfilled. But anyway, if you do it like that way, you get a computationally efficient classifier, usually performing good, particularly with limited training data, and it is also robust to missing data points. But well, the most easiest way to understand how classification based on training data would work is, from my opinion, actually what is called the nearest neighbor classification or classifier. So suppose we have a feature vector composed of only two features, the x1 feature and the x2 feature. And usually we have much more, but this is what we nicely can visualize. And then we have our training data, which we can plot here in this x1 and x2 space. And that is our measurement. And we plot that measurement in this space, and then we seek for the nearest neighbor. And if the nearest neighbor is a red one, we assign red to that one. And if the nearest neighbor is blue, we assign blue to that one. And it makes clear that this one here is easy to compute. You just compute the distance from that point to all the others. But that one certainly is affected from outliers. Suppose this is all blue here, and there's just one red point in between, and it may happen that this one is closely related or neighbored to that outlier. You would assign the outlier. And in order to get a more robust classifier against outlier, we use what is called the k-nearest neighbor. That means we have a set of nearest neighbor, 3, 5, 7, but usually 3 or 5 are used. That is already enough. Why is it an odd number of neighbors? Well, then you clearly have a majority that you can solve. So we have this, our data point. In this case here, from the 5 nearest neighbors, 3 are blue and 2 are red. So we assign to blue. And another way you could do that is that you are computing all of the red points into a representative, and you compute all the blue points into a representative, and then you only need to calculate 2 distances in that case with the 2 features and the 2 classes, and you end up with a classification. Yeah, so the advantage of this simple classifier is we don't have any model assumptions, and we are able to handle complex data. Of course, we are sensitive to noise, in particular with one nearest neighbor classifier. And well, if we are not using the prototype neighborhood, we are might end up computational quite expensive, because you need to calculate the distances between the measurement and all the training data. Now, here's some examples from the pictures taken from Wiki. So these are our data points, and if we have the nearest neighbor classifier, we see that a lot of outliers here are determined maybe wrong decisions, because this is the green area, and if you use a 5NN classifier, it becomes smoother in that case. Yeah, but the performance, as you can imagine, in higher feature spaces is limited. Yeah, and so another classifier which becomes quite popular in the 80s was what is called the support vector machine. That is a supervised machine learning algorithm for classification and regression, which initially uses a binary classification problem, so 2 classes. And I have plotted these 2 classes again. We have the X1 and the X2 class features, and the 2 classes red and blue. In that case here, the classes are separated perfectly, and you can find a line separating these classes, and of course there could be different lines here. And the question is which line is the best line for separating, and that is calculated by what is called the support vectors. So you position the line such that the lengths of these 2 vectors here become maximal. Okay, so that is how this classifier works. It can use binary classification problems and end up with a linear thing. But most problems, as you can see in this drawing here, are maybe not linear. So in order to separate these classes here, we cannot find a linear curve. And the idea behind this support vector machine is, well, if we transform our data in an even higher space, we might find a hyperplane clearly separating this data. And I think this is here nicely illustrated. So if you add the 3rd dimension, you might be able to separate, as is drawn here. So all the blue things are on the top, and the red things are on the bottom. So, and that is what usually is called the kernel trick in this support vector machine. So you transform your data with what is called kernel function, and several kernel functions have been used. Now, if you use the Gaussian as a kernel function, you basically end up in an infinite dimensional room, where you might find the hyperplane and project it back to your initial space in order to make the decision. Yeah. Well, as I mentioned, a support vector machine is only for two-class problems. Sometimes or mostly we have more than two-class problems, and then we can still use the support vector machine with two different strategies. The one is split into single binary problems. The one strategy is 1 against 1. That you can see here. We have the blue against the red. We find this line here. We have the blue against red was that line. Blue against green was that line. Red against green is that line. And based on that, we find separation between these, in this case here, 3 classes. And the other thing is that we are doing 1 against all. That means here the red against green and blue, blue against red and green, and so on. And using these two different principles, we actually are able to solve multidimensional classification problems, not only binary classification problems. And last thing in this machine learning part is then what is called perceptron. It is an artificial neuron. And the idea is to mimic with computer algorithms how our brain is doing decisions. And as you might know, our brain is composed of neurons, millions of these neurons, which are interconnected to each other. I see these German names here, but we have the dendrites, which are the input of the cell. We have the cell body, which computes from the input. And then we have what is called the axon, which is the output of this cell. And in the 80s, that was mimicked in the computer algorithm. So usually we have a system like that, where we have several inputs which are differently weighted. Then it sums up. And as you might know, here, depending on the input of the electrical voltage, which is given to the cell. If it is above a certain threshold, then the output is generated. And that is the same here. We have this threshold function, which is generating, and as thresholds, the sigmoid function is used, tangens hyperbolicus, or in the neural networks nowadays, also this what is called rectified linear unit or ReLU layer. So using a system like that, we try to mimic the decision making, and that is maybe the next step. Then deep learning. We start with the neural networks, understand how these neural networks are working, and then what is the difference between these neural networks and the deep neural networks. And of course, then also look for what is called recurrent neural networks. But let us start with this perceptron. And now we can use more of these perceptrons interconnected in order to build a neural network. And that was the neural network, how it might look like in the 80s. So we have input layer, we have an output layer, and we have what is called a hidden layer. This topology is constructed that each node here is connected to all the other nodes. And whether there is information flow from here to there is, depending on the weight, of course, the line here has. So the single layer perceptron might have one or even none of these hidden layers. So these were very yeah, small neural networks with just a few number of neurons, which was what the computers in the 80s was able to handle. So the parameters we have is simply the number of nodes in the hidden layer, if there is one. The structure, as I mentioned, is fully connected, and feed forward, so it is clearly processed from the left to the right. So you can move the information here through the network. And then we had this multi-layer perceptrons, which is also in the machine learning, not in the deep learning yet. The number of hidden layers at that time was usually restricted lower than 5. Here, well, we need to decide on the number of hidden layers and, of course, to decide on the number of nodes in the hidden layers. And as you can see here, if each of these lines is one weight parameter which needs to be learned, the more hidden layers and the more nodes per hidden layers you have, the numbers of parameters is becoming exploding. Let me illustrate that with one example here. You will find this example in the internet. That is how to, well, read handwritten numbers or letters. So this one here might be a 6, this one here might be a 4, not a 9, whatever. And the question is how the neural network is doing that. The first thing is we need to extract features from these images. It could be the number of pixels being white against those being black. It could be the bounding box. It could be something. We will come to this problem of the features later. But then we end up with a network here where in this case we have an input layer. That means the dimensionality of our feature vector is more than 700. And the output layer is the different classes, the numbers we have, so 10 layers. And we have some classes here in between, and the weights hopefully are that such that, for instance, if this figure is calculated to the feature vector we give in the input layer, then the node corresponding to the letter 2 in the output layer gets the highest output. But how do we train a network like that? How can we find all the weights? And for that, of course, we need the training data, where we have feature vectors and classes assigned to each other. And that is here. The algorithm is called backpropagation. We have our network, we have our output nodes, and we have the ground truth information. And as we can see here, in this example, of course, all the outputs, perceptrons are activated, but with a different volume. And in that case here, well, the right one has already the highest output. In that case, the decision would be right. But we want actually to form the output that it really reflects the ground truth. And that means we have differences here. That is 0.2 too high, it is 0.1 too high, and so on. And based on these errors, we calculate the errors here in the output layer as compared to the ground truth. And then we have what is called the loss function. And we recalculate the weights here in order to have the loss smaller. And from that, of course, we can backpropagate to the next layer and recalculate the weights here in order to have the weights here better, in order to have output better. And that can be done for all the layers, basically. And then, of course, we have many training data. So we need take the next example from the training data and do this calculation and error backpropagation, modifying all the weights. And that is done then for all this training data in a row. And here is an illustration that shows the performance depending on the number of hidden layers. The more hidden layer you have, the more complex data you can understand. And if you see here, it's a hard computational problem, because the two classes are looped into each other. No chance with 3 layers, better chances, but not good chances with 6 layers. And then here with 10 layers, we see that the neural network is really able to adapt on this problem. However, that also illustrates if the network becomes more complex, and it might learn too much on the training data, which we called overfitting. Okay, so that was so far, neural networks. And what is now deep neural networks? Deep neural networks is actually the number of hidden layers. Computer systems in the 2000s become more powerful, and we were simply able to handle more complex networks. This is a nice graph showing different network topologies. There are a variety of how you can interconnect these perceptrons. The number of hidden layers, the weights and so on might explode if you are using a large number of these neurons. But if we look to this, all these topologies, I want to point out some things here. The one that we have here is that there are interconnections between the layers. There is no error in this, but the meaning is that they go backwards. And if we have these backward things, then we can put something like a memory in our model. So that stage here gets the history due to back looping things. And another thing here is a mechanism I called contraction and expansion. So you see that in the middle of the hidden layer, the number of nodes are really small, but then they become large again. And that principle is also used in what is called convolutional neural network. I will explain that in more detail tomorrow when it comes to image processing. Okay, but let us look to this mechanism here where we bridge information back. So that is particularly useful if we have to process sequential data. Vital signs measured at once a second and so on. We want not only to classify due to the absolute value, but we want to see, well, what is the change indicating us? Text, speech, and time series, ECG, for instance. This is data where we need the history. And the idea is to loop back. That means the output of the node becomes the input of the same node in the next iteration. Those we have these backward loops, and this backward loop can be unrolled. If we look to the t, which is the time. So we have the initial stage, which is 0, and well, the 0 stage goes to the next classification, which is the 1 stage, t equals 1. And it also goes back to the t2, and it goes back to the t3, and so on and so forth. That means the unrolled recurrent neural network becomes large in the dimensions of the time. And here's one example. If we look to the sentence, what time is it? Yeah? The colors here might indicate when you read the first word here. Yeah? The node has the information from the first word, and then the second word comes, and the third, and the fourth, and so on. Yeah? And as you can see here, the portion of information in the history, of course, becomes smaller in that mechanism. That means we are able to model something like memory in these neural networks, but the memory we can model in this basic principle is just a short-term memory. So like mine. You tell me your name, I will have forget it in the next moments. And then a particular network architecture that is called long short-term memory. That is how to extend this short-term memory idea such that we actually have a long-term memory. And that is due to modeling some hidden states here. We have the input vectors at different points of times. We have these recurrent neural network here, and we actually model a longer memory by this network architecture. And then it comes to the next stage, which is the general intelligence. So what is general intelligence? We can say that is artificial intelligence that can create new content. Maybe new text, new images, new music, new videos, and so on and so forth. It learns from the patterns and the training data and samples from them. And it just, I like this picture here that was produced by my students with DALI as a GTP4 based program, and the prompt was to create a creative and humorous illustration for a paper on horse hoof autonomy. That, by the way, will be the example here for tomorrow. And I like this very much. You look the foot here with 6 toes and so on. So it's nicely composed, but it's not perfect. The students here all are horses. What they have in the book is not readable. The time here is mismatched in these 2 clocks and so on. I like it. And the question is how we can create networks able to end up with things like that. The key term used here is what is called foundation model. Foundation model has been trained on a vast data set, and it can be applied to a wide range of use cases. So far, we trained the network with particular data for a particular task. And now we train networks with what we get and see at the end what these things are able to do. And basically we have 2 things. The one is the large language models, and the other is the diffusion models. The one is given for text and natural language processing, and the second one is used for basically images. But I think what is very important here with the large language model is that they actually are stupid programs calculating statistics. So if we have a large language model here, and we have a sentence like Paris is in a city in, then from all this training data, which is the internet and everything what was available, it calculates its likelihoods, which word might be the best fitting here. And in that case would be France, because it has the highest percentage. And that is how these networks work. Simply doing statistics. And statistics based on the training data. Training data is always data from the past, not from the future. However, it works pretty well in generating texts and images, answering questions, reasoning, summarizing, translating between the languages, and so on and so forth. Very powerful tools for that. If we want to look inside here, how they are built, we end up with a network architecture which is called a transformer. Actually, in 2017, the transformer was presented by Google. That is basically how it is composed. I will not go too much into detail here, but we see a lot of tricky selection of stages of the processing. And we also find the idea of having layers in the middle which are not that dense in terms of the number of neurons, and then expand again. We have loops here, and of course then we do not use only one of these architectures. We use more. So 1 year later, BERT was born with Google. It stands for bidirectional encoder representations from transformers. I think what is interesting is the number of parameters. That BERT thing here was 340 million parameters and was trained by about 3 billion words from some training data. Then we have GPT from OpenAI. The first version here was built with multi-heads. So we have 12 heads here in one transformer, which means the basic module, and actually 12 of these stacked together in parallel. The architecture of the GPT-4, which is used by now, is not known, but what we basically know is the number of parameters, who is roughly 500 times of that before, and also the number or the amount of training data that is used here. That is how these systems are built. If we look to images and creating images, we have basically what is called the diffusion model. So in the training phase, we start with an image and we add noise to the image. More and more noise, which you can see here in the forward diffusion process until we end up with only the noise. Noise is entirely covering the picture. And then in the backward loop, we try to train the network such that it can reconstruct the picture out of the noise. And if you do that for a vast amount of pictures, then you end up with networks which are able to actually also compose things from different images. That is the architecture of the diffusion model. And as we had, for instance, in the here. I didn't mention that. So in the large language model, we of course need to give the input to the model, the pre-trained model, what our problem is. And the same we have here in what is called conditioning. So the input that makes this architecture adaptable to different problems. Okay, so having said that, we go to the learning strategies. These terms are important. We speak of supervised, semi-supervised, unsupervised, and reinforcement learning. And what are the differences here? Supervised learning is what we used all the time in this lecture so far. We have input vectors, which are known output class, and the model learns the input-output pairs. Use cases classification or also regression, but for this lecture here we will stick on the classification problem. And the challenges are, well, the labeling of the training data is time-consuming, costly. We need large data. If we want to train 340 billions of parameters, you need at least 340 billions of trained data, which of course you cannot generate. And this is the principle. We have the labeled data here, we have the labels, we have the algorithms, we do the processing, and in the output we have the classes assigned, and the supervisor, that is where the name supervised learning comes from. He looks to what is the training data and the desired output in order to guide this process. Then the problem is creating these ground truths. So usually in our problems, we only have a small amount of labeled data, but we may have a large pool of unlabeled data. And that is what we are using in semi-supervised learning. That means we use the small amount to, well, label the unlabeled data points, hopefully correctly, and then use the entire labeled training data to retrain the model. That is used in speech recognition or image classification. And of course, the challenges are that our pseudo-labels here might be incorrect, and then reinforce mistakes. And of course, we are sensible or sensitive to how our small amount of labeled data is composed. That might influence the outcome then of the entire network. But for example, it's like this, that we have the small labeled data set. We have the large unlabeled data set. We train the model, do the classification, retrain the model here, which is illustrated by the loop. And then we have the pseudo-labeled data and the final model and a large labeled data set that we use for classification. But what if we don't have any ground truths at all? We still can use the networks in what is called unsupervised learning. That means we learn the structure from the data without any labels. And the problems or use cases here are clustering, dimensionality reduction, or anomaly detection, finding outliers in the data or groups of outliers. Challenges, of course, no ground truths. And that we end up with a classifier that might discover some important patterns. How does it work? Well, we have the data, which is mixed of different classes, and we try to adopt the network such that it is forming these classes. And the last learning mechanism I want to introduce here is what is called reinforcement learning. Reinforcement learning, the idea here is to mimic again how humans or animals learn. And we learn by rewards. So if we do something right, our parents say, "Oh, good," and so on. That is the reward mechanisms. So the idea is that we model the learning process with an agent that interacts autonomously, and depending on what he is doing, he is awarded or not awarded, or more rewarded or less awarded. And of course, the agent tries to find the highest award he can achieve. So we have the agent, which is the learner. We have the environment, that is the world the agent is interacting with. We have the action that is generated by the agent living in the world. we have the state, which is the current situation, and we have the reward, which is the feedback from the environment to the agent based on his action. And the policy, which is the action strategy for choosing new actions based on the current stage. And with this, you can end up with an algorithm that the agent analyzes the current stage in the environment, and based on its policy, he decided on his action, and then he gets the feedback from the environment in terms of rewards, and based on that, he updates his policy in order to maximize the reward he can get. The challenges in this reinforcement learning is exploration versus exploitation as a trade-off. If I already know that I get, say, fairly good reward doing something, what makes me trying different things, which might end up a higher reward, but bearing the risk of getting no reward at all. That is a problem we need to solve. Also the inefficiency of some samples, and how to design actually a good reward signal in this environment. But anyway, we can apply this to a lot of examples. For instance, if you train your dog, in that case, your dog would be the agent. And it needs to learn sit on a certain symbol. When he's doing that, he gets a reward. Maybe some food, maybe some oral rewarding, and so on. We have game playing. The agent wants to learn to play chess, but by playing against himself or other players, which then are the environment. And a last example here might be from robotics. The robot, which is the agent, learn to navigate the room, which is the environment, by doing autonomous interactions. So that is basically the world of artificial intelligence and machine learning. And I want to use my last minutes. I was told that as we started early, I'm allowed to speak a bit longer. So I want to go a few minutes on what is called ethical AI. So understand the aspects of ethical AI, in particular for computer-aided diagnosis, and if you translate those algorithms in clinical routine. And I'm pretty sure that these topics will be addressed in the summer school in some different talks also. But anyway, what is meant with ethical AI? And there are some basic limitations, which we already understand, hopefully, from what I was telling you this morning. If we apply AI on medical data, it suggests what is usually suggested, based on the past of the training data. It is not suggesting what maybe would be right to do, because it doesn't know. I didn't go in detail of the phenomenon of hallucinations. What are hallucinations? Well, these are things which are suggested by the network, generated completely artificially, sound logic, but are not really that. And if you use LLMs, for instance, for text generating, it happens frequently that references are generated which are not existent. If you want to read more, you may have a look to this report from the task group of the American Association for physics in medicine, not physicians, but physicists. Recommendation on some practices in machine learning. And some problems which are addressed here, of course, are the training data. I think you have learned about the importance of the training data, and what if the training data is not representing, well, the group of patients you're using the neural network, with respect to gender, age, and all these things, ethnics, and so on. Regarding the model development, the performance, a long-term application, what if the data shifts, problem, for instance, in all these machines accepting money, not in terms of coins, but in terms of printed paper. Yeah, what is the name for that? I don't know. But huh? Bills, yes. The pesos, yeah. But not as a coin, but as a paper. These, of course, are printed, and the printing process may change colors over the time, such that the machine is not accepting newer ones because it was learned on older ones. So what is the data is drifting, and how to manage these problems. And of course, also you need to think about the resources these neural networks are needed for training and for using, with all this computation and computers behind that, with respect to electricity and also to water resources for cooling the systems. In this paper here, we separate different tasks in medicine from risk prediction over, of course, disease detection and characterization, which is the diagnosing, and then treatment. And if we look to the diagnosis, we have computer-aided detection. That was a term I already introduced. Computer-aided triaging, which means the computer helps to sort out and what is called ruled out. The different paradigms here is for what the computer-assisted support system is used. So it can be used as a second reader. That means second opinion. Here, we try to improve the decision-making by the medical expert, and usually provide the output of the automatic analysis after the initial reading of the physician. You can do it as a concurrent read. That means the output of the system is available for the expert at the same time he does his initial representation. Helpful also is the triage. That means the medical expert still reviews all the cases, but in a different order. The computers, the decision support system tells the physician, take this one first, because this is the most important one. And then we have rule out, where the systems may reduce the number of reads from 1,000 to only 200, which are the most likely important cases, while the 800 are normal or regular cases. And that then the physician will not look to these rule-out cases at all. So these are really different use cases you need to take into account when you look to the development process. And what is important, if you are developing a system based on AI for the use of physicians, is what is circled in this case here in the translation to the clinics. And this one, or the problems here are more elaborated in this paper from the same working group. And basically, it's quality assurance, quality control, and acceptance testing, which is important. So determine the baseline for your performance measure and do ongoing monitoring of the performance, whether it changed over the time. The quality control before the installation, after the installation, and then in the routine application, which is, of course, related to the quality assurance. And also a very important point on the accepting of these systems in the medical use. You need a particular training of the physicians that they know how to use these systems, what they can do, what they cannot do, and how to understand what they are putting out. So that is what is called explainable AI, and I'm pretty sure will be addressed in future talks here. Of course, you need to define carefully your exception criteria. Okay, so let us conclude the talk. I talked about, give a short summary and then 3 messages for taking home. So artificial intelligence covers expert systems, machine learning, deep learning, and general intelligence. We had the different classifiers which are built in these machine learning systems. In deep learning, we talked about the network architecture and also the recurrent neural networks, which loop back information and be able to, build something which is called memory, or something like memory. With respect to generative AI, we talked about large language models and the diffusion models. The one is more for text, the other is more for images, and also generating images, but also segmenting images and so on. I will come to that part here tomorrow in the lecture. We have the different learning strategies depending on the ground truths we are having. And I briefly looked to the aspects of ethical AI in terms of bias, depending on data bias or representation bias, algorithm bias, and so on and so forth. You will find a lot of problems with the biases here, and also drifting data. And I think if we are looking to computer-aided diagnosis based on AI, the different paradigms you can use the AI for are important to understand and are important to differ. And translation to the clinics. Here is another more time-related diagram where you can see the development. Perceptron here was in the 60s, support vector machine in the 90s, and deep neural networks in 2006. But what are the most important messages for you maybe to take home? Generative AI is the descriptive statistics, basically. So it represents what has been learned, and that is what is the existing things. So it's only the past, and it cannot develop new ideas. Deep learning can be a powerful tool in the clinic, of course, but you need to be aware of the problems that may be related, bias and drifts, and the things we briefly addressed. Composing the training data set of AI is very crucial. And the problem is, it is often unknown. If we are talking about these large models, nobody has no idea what data actually has been used in order to train these models. And still, you use it, although you're not aware of these biases that may be in the data. And that's it for this morning. I thank you for your attention and hope you liked the lecture. And I think we are still ahead of time, so if you have questions, I'm happy to answer them.
Thank you, Dr. Thomas, for your presentation. I think you made such an enjoyable presentation for everyone. Is there a question that anyone would like to make from the audience?
Hello, thanks for the speaker. I have a question, and it's about this risk that you have, or bias risk, etc. As you mentioned, I'd like to know if there's something like a surveillance committee or similar, like supervising the uses of AI in this medical aspect, and or how is this fighting in the use in the real life?
Well, it's a difficult problem you are addressing. Yeah. So the one thing is we might know what is used for training data and how it is composed. Yeah. Then, of course, we can analyze whether whether certain groups of patients are adequately represented in this training data. So we can analyze that, but as I mentioned just in the end of the talk, in particular for these large models, we actually don't know. So there is no methodical mean to address these problems. The only thing is that you can observe the performance, and you need to do that continuously, because also the data may change. I think in the examples we will learn in the next lessons and also in my next lesson, if you're able to train your model based on data, not only from one data source, but from more data sources, the performance of these models generally increases. So one key, for instance, is doing that. If you have, for instance, MRI images, it's good to take not only from one machine. It's good to take not only from one hospital. It's good to have a variety of things, to have your model not learn specific things. Sometimes the classifier of these models are more determining the machine which was used in order to make the image, but not the illness which is in the image.
Thank you for your answer. Is there another question?
I think he was first. Not you.
Okay. Thank you very much for your talk. It was very, very interesting. I agree also with this last point that's composing the training data set is very crucial. I have a question for, like, in medical context, how much problems do you have with privacy issues and with this, maybe not necessarily classified information, but information that maybe patients don't want to disclose? How do you deal with that in this context?
I haven't addressed this in this lecture here, but I think you're referring to the data we use to train, which of course is taken for individuals, from individuals, which are, the one thing you usually do is anonymization. However, if the data is rather complex, you might be able to identify the person based on the records. Particular, if you're using genome data, which is very unique for a person. That is the problem of privacy is not only that you know the identity, but if you are able to reconstruct the identity, it's the same problem. That is a problem. And what we are doing in medical applications, try to have that chance of re-identifying the person becoming as low as possible. And that is, if you form the feature vector, you need to take care that you don't have unique feature vectors, but at least a few numbers of individuals deliver the same feature vector. And if this number is, say, larger than 10, and there are measures to calculate that, which I have also not addressed in this short lecture, but using these tools, you can at least give some basic security of personal data.
Okay, thank you very much.
Okay, there's another question.
Thank you for your lecture. It was pretty interesting. I was wondering, when you say that the AI cannot develop new ideas, but I was thinking about the learning process of the AI, that it was just in data, sorry, recollecting. So isn't the AI capable of suggesting like new treatments just based in probabilities of data recollected, and then just analyze the things that it's recollecting and being supervised by someone else, and just generate the not new ideas but ideas based on the past data?
Yeah, well, in general, I would say no, yeah, because it is learned from the past data. Yeah. Of course, it could generate new images or new text, which has been existing before, but based on the statistics of the past. It's not fantasy we might have, yeah, coming up with complete different new ideas of things. That is, at least as far as I would say, not possible yet with the network tools we have.
Thank you so much. Right now we have a question from the Zoom meeting. It's from Pedro Alberto Mendoza Pablo. He asks, do you know any specific applications for the use of AI in public health problems like obesity, diabetes, hypertension, drug use, etc.? And if so, with what analysis strategy?
Can you repeat the last
Yes.
part of the question? So it's on where
Specific strategies for...
are used with artificial intelligence in public health.
Yes.
Yeah. Well, I think most popular examples are generated during the COVID pandemic. I know from systems where X-rays from the chest have been passed through neural networks in order to identify patients which are likely suffering from the COVID disease. And I know that these systems, which has been in research, have been looped into the regular workflow, for instance, at the university hospitals in California and San Diego. That was amazing because they have this research project at the time where the disease outbreak was, and they were able to put it in the clinical routine at that time. And I think also analyzing other parameters in that case are good examples where AI already was in use.
Examples that were ahead of time, but right now we hope to have it worldwide, right?
Yes, of course. There are a lot of FDA-approved AI algorithms, basically an image processing, image analysis, reading mammographies is one of the examples where these systems are used. And I think it's important to always have a look what is the paradigm for the use. Second read, concurrent read, and different things.
And there's another question from Emma Jimenez. How much time it would cost to train an AI to predict certain illness and treatment immediately, especially for the countries where funds are not going through that way?
Well, there are two different things. The one thing is to train the model, and the second thing is to apply a trained model. Training the model takes a lot of time, or you need high-performing computers to shorten up the time. But as you can imagine, if you are modifying millions and billions of parameters, that is a lot of computation. However, there are models available, and I will come to these models in my example tomorrow, which perform the task on, for instance, a mobile phone more or less in real time. And the calculation actually can be done on the mobile phone without any internet connection, which might be the background behind the question. If you want to apply these systems in settings where,
Make it accessible.
genau.
Yes, it's my turn. I'm so glad to hear there are questions coming from the cloud. Can you say a little bit more about generative AI not being able to develop new ideas? Is it purely a combinatorial thing or something else?
I actually don't know about any example that one could report on where AI comes up with disruptive new ideas of how things are to be modeled, how the reality is. I'm not aware of those, but I'm...
Speaking to the last question about public health and introducing health in underserved areas, what about in drug discovery and then applying the drug to a population or an individual?
Well, I think this is a question for my colleague Tim Kafrowski in his lectures. He is more in the...
I have a backup question
yeah.
on nuts and bolts type of thing.
Yeah.
When there are anomalies like hallucinations, is there any kind of troubleshooting? I mean, what do you do to a model, a large language model that's hallucinating a little too often?
Well, yes. What can you do?
What can you do? All right.
The first thing is you realize that that happens. If you understand that there is a frequent occurrence of these hallucinations, that is a good point to start. And then you can try to retrain the model such that that not happens. But again,
training.
Training. That is the issue. And for training, you need data, and then it loops back to how to compose the data and how the data is composed.
Thank you. And we have 2 more questions from the Zoom meeting, and this will be the last one. And then
There's
we will
also
have the
one in
break.
yeah.
We will have the break, and then you can ask him directly during the break, and you can all discuss with Thomas during the break. Do you think AI should be moderated by a corporation or government, or this already exists? And the second one is, I want to know, what do you think is the biggest challenge when implementing tools or programs in a hospital?
Okay, so the first question was about how to regulate AI in clinical use. In the United States, we have the FDA who is approving this algorithms. In Europe, we have, I would say, even stronger system for getting approval. What the big issue right now is if you have AI system that is learning over the use. So once you have generated a static model, that may be evaluated by FDA and other organizations, and then you can use it. But if the model learns from what is going on, if it is adapting, if it is able to cope with drifts in the data, then the model changes all over the time. And so far, neither in the US nor in Europe, we have regulatory ideas how to cope with such type of systems. So in Europe, for instance, you will not be able to get approval for such a system right now, according to the rules we have.
Thank you so much for your answers.
I think there was a second part of the question, but you need to repeat that.
Okay.
If I need to answer it right now, or
It was the hospitals question and the government related one.
Yeah, government-related
what-
was,
what can
and
we-
the part for the hospitals, what
What
was?
can we do to implement, how can we implement these kind of systems in a hospital? Like, what are the challenges and?
Yeah, well, there was one slide I just briefly show at the end, yeah, where you have the workflow of how to develop it and how to put it in the practice. And I think it is very important to have the users, the physicians or the medical professionals, must not only be physicians, in the loop, in the developing and implementation phase. That you need to define the criterions, how to measure the performance of these systems, and how to monitor that regularly.
Thank you so much. Can we give an applause to Dr. Thomas?
Thank you.
Thank you so much. If you have any further questions, you can still talk to him during the break. We will be back at 11 o'clock to have Dr. Tim Kaprowski to give us his next lecture. Thank you so much.